So we will look at 6 different types of commonly found steady flow devices. In other words, we are looking at 6 common open systems that we usually deal with in engineering. Okay, so you can see that we have nozzles and diffusers, compressors and pumps, turbines, throttling valve, mixing chambers, heat exchangers. So for those of you who have started so for all of you actually, when you are starting lab this week, for some of you later, you will be dealing with this one and this one lah. So you will see some of the example of these things. Okay, so the first one that we look at is actually nozzle and diffuser. So in simple terms, nozzle is a device that increases the velocity of a fluid at the expense of pressure. Diffuser is a device that increases the pressure of fluid by slowing it down. Technically speaking, also, so slowing down and increases the velocity. So these are their functions. Okay, so these two, they are same thing. Okay, as in theory wise they are the same but the opposite thing. Okay, nozzle increase velocity, diffuser reduce velocity. So nozzles and diffusers are commonly utilized in jet engines, rockets, spacecraft, and even garden hose. So garden hose is one very simple example of nozzle. Otherwise, yeah, in all these applications, engine, rocket, spacecraft, we do use them. But of course, we are not looking into them here. So here, we are looking at how we can analyze nozzle and diffuser. Okay, so energy balance for a nozzle or diffuser. So again, we start with our standard energy balance equation. So like I said, we always start with this equation. Okay, so this equation here. Okay, so now one thing that you have to bear in mind here, for all of these special cases or examples that I'm showing you now, I'm just showing you the common way of how we analyze. So ultimately, it still depends on the situation, meaning things can still change lah. So let's say, in this case, now when we are dealing with a nozzle and diffuser, one thing that you definitely cannot cancel off is, so can you guess which terms are the one that we cannot cancel off here? So usually we need to simplify. So in open system, usually what we do is we write out this equation. Then you simplify the equation so that you can analyze it lah. Basically, take out the terms that doesn't exist. So for nozzle and diffuser, right, which term do you think that we cannot take out? That you should never take out? Velocity, Ke. Okay, why? Because that's their main function. The main function of diffuser and nozzle is to affect the velocity. So in this case, so even though in the previous slide we did prove that velocity or Ke usually are not too significant, but for this case you cannot ignore them because that is their main function. If you take it out, then the nozzle and diffuser don't really serve their function anymore. Okay, so in general, this is what we can solve. Q in, Q out. So here we are assuming an ideal nozzle or diffuser. Okay, so again, depend on the question. Let's say if in the question we say that during the acceleration process of a nozzle it loses heat, then of course you keep the term lah. But in the ideal case, an insulated nozzle or diffuser, we can cancel this term off because it doesn't really serve any purpose. Work also, this one definitely will get cancelled off because we don't need to supply any energy for a nozzle or diffuser to work. They also don't generate any energy or work. So work out, work in definitely cancel off. So generally speaking, we don't have nozzle or diffuser that would change any height. So gravitational energy term will also cancel off. So this is what we are left with. H term, most of the time we don't cancel one lah, because you will have flow energy, you will have change in internal energy, so H term will always be there. So we never cancel them off. So generally speaking, if you have an ideal diffuser or nozzle, this is the equation that we use. So again, don't memorize. remember, just need to remember this full term. Cancel off one by one, based on logic, and also whatever that's given to you in the question, basically. Alright, so this is the case for a nozzle and diffuser. Clear so far? Okay, next up, we look at compressor first. So compressors and pumps. So here we actually have three different cases in a sense. So we have compressors, we have pumps, we have fans, and these are devices used to increase the pressure of a fluid. So this one, sometimes you might have a slight misconception because usually what we observe is velocity. So we will always think that compressor, pump, fan should increase velocity, right? But their main function is to increase the pressure, not velocity. Always remember this. Velocity does not necessarily change because density can change during the pressure change situation. And also it's not a significant part. Their job is to increase pressure. So always remember this. So work is supplied to these devices from an external source through a rotating shaft. Okay, now one question here. I think fan, we all know. Fan is not so commonly used for us because it's just a normal devices. Like, we don't really use it in like engineering sense. You use it just to increase airflow, that's all. But they function the same, right? Because fan, when it turns, it creates a pressure difference. That's why airflow. What is the difference between compressor and pump? Like, why do we have two different names? So function-wise, they are still the same, okay? But for us, for our application, even though it might be a bit counterintuitive to you because that's not the term that you use in real life for some of the things. But compressor, this one more common. Compressor, usually when we talk about compressor, let's say if you go to the lab, you are looking for compressor. Compressor supply air, right? So compressor works with gases. Pumps work with liquid. That is the general idea that we use here. So when we talk about pump, we are talking about something that works with pure liquid. When we talk about compressor, we are talking about something that works with pure vapor or gas. That's how we separate that. So maybe a bit counterintuitive to you because when you want to refill your bicycle's tire, you also call that thing pump. Technically speaking, you don't call it compressor, but yeah. But in general, in engineering, pump is the one that works with liquid. Compressor works with gas. That's the idea. Okay, so we supply work to these devices. So basically, you use power to power these devices, and then these devices will supply that power to the working fluid, whether you are talking about liquid or gases. So for this case, based on just these two definitions, you should know one thing, which is, of course, work in, it cannot be cancelled off because we are supplying energy to the fluid. Okay, there's no pressure term here. So, but of course, this pressure term will determine the change in the enthalpy. So for this, again, ideally speaking, this is not an ideal case. A pump or a compressor, in actual case, will always have Q out instead of Q in. So there's no way that is you have a Q in this case. So it's Q in we can cancel off. It works with work in. So work out cancel off because pump doesn't generate power. We are always looking at, how should I say? We are always looking at these things, again, remember, from the perspective of the fluid, of the substance. We don't look at it from the perspective of the device itself. So, of course, if you look at the device itself, then yeah, pump supply power, right? So that's work out. But we are looking at it from the perspective of the fluid. The fluid receives energy, that's why the pressure will increase. So we will have work in, no work out. Of course, again, so like I said just now, velocity mostly is very negligible, and that is not the main purpose of pump. So we will cancel this off, again, unless the question tells you otherwise. So then Gz, which is the potential energy, will also cancel. This one, most of the time we cancel it off. So you are left with this equation. So this is not an ideal equation actually. This is an actual equation in a way, because I mean I think you should be well aware as well lah. Pump compressor, as it works, it will actually generate a lot of heat as well. So that's why we will have Q out. But of course, if let's say do I have this equation? No. So let's say if you have an ideal case, okay? So let's say if you have an ideal, well insulated pump, then we can cancel this term off. So you will be left with work in equals to m dot h2 minus h1. So this is actually the equation if you have an ideal insulated compressor or pump. So for those of you who have went through the first lab, so and some of you going to face this week, when the one that if you have conducted the refrigerator trainer lab, you will see that this is the equation that we use for the compressor. I think only a few of you have seen it, but yeah. So this is how we arrive at this conclusion. So for those of you who have not gone into lab, you can also bear this in mind when the tutor explains to you how you find the energy change. Basically, it's from this kind of equation. We cancel off, then we are left with this equation. So this is the ideal case when you have an insulated compressor or pump. Okay? Alright, then now we move on to the next slide. So the next slide we are looking at a turbine. A turbine is actually the opposite of a pump or compressor in a way. So a turbine is a rotary engine that extracts energy from a fluid flow and converts it into useful work. So pump, we supply work to the fluid, we increase the pressure of the fluid, then the fluid will flow in a sense. So turbine, a liquid will flow to a turbine at high pressure and temperature, then those things will reduce and it will extract energy. So then the turbine will turn, it will power a shaft, and then we generate energy. Generally, that's the idea behind turbine. So, like I said, turbine is the opposite of compressor. We can solve work in. And we can solve the velocity term because it's not very significant. GZ also cancel off. Now, so here you will see that we actually don't cancel off either Q in or Q out because we don't really know whether it will gain heat or release heat. In general, it will release heat because, or let's say if we are talking about a turbine at a power plant. The fluid that flows through the turbine will be at very high temperature, so it will lose heat to the surrounding. But if you are talking about like water turbine at the river, then it probably will gain heat instead. So it's not a fixed thing here. So which is why this is a general equation. But of course, again, same thing. If we are assuming that the process is adiabatic, then we can, or the whole turbine is well insulated, then we can cancel off these two terms as well. And this is what you are left with. So this will be the ideal equation for a turbine. So, the question will tell you. So if it involves like heat loss or heat gain also, it depends on the question. Because in real life, all these things is not, like I say, it's not a fixed term, so there's no way to tell. I mean, there is a way to tell, but you have to measure lah. You have to see. So in exam, of course, we are the one that tells you this. So otherwise, this will be the equation. So the process through the turbine, right? We actually call it an expansion process because again, we say that this is the opposite of a compressor, right? So compressor, we have a compression process. So when the liquid flows through a turbine, we call it an expansion process. Okay, the volume actually will change. The specific volume will actually increase a bit. Will actually increase. So that's why we call it an expansion, because the volume will increase. Pressure will drop. Alright, so now we look at what we call throttling valves. So throttling valves, again, is something that will appear in your lab. So throttling valves are any kind of flow restricting devices that cause a significant pressure drop in the fluid. So what is the difference between a turbine and a throttling valve? Because you can see that throttling valve will also cause pressure drop. Turbine also cause pressure drop. So the main difference will actually be the function. Turbine, the main point is to extract energy. But in a situation where, let's say you want to reduce the pressure of a fluid, but you don't really need the work out, because turbine itself is a very expensive thing and very complicated thing, then we can use what we call throttling valve to basically just to throttle the flow to reduce the pressure. So the pressure drop in the fluid is often accompanied by a large drop in temperature. So, and for that reason, throttling devices are commonly used in refrigeration and air conditioning applications because we want to reduce the temperature of the fluid. So these are some of the examples of throttling valve. An adjustable valve, basically you just adjust it halfway, then the flow will get throttled, then pressure will change. So porous plug is one thing, capillary tube is also one example. So in essence, it's just a normal piping, if you think about it, but we change the flow. So for a throttling valve, based on what we explained here, again, it is just a normal piping, right? Like let's say adjustable valve. All you need to do is just turn it halfway, the flow inside will get throttled, pressure will change. So all these things depends on the construct inside of the pipe. So for a throttling valve, actually, we won't, again, we are talking about ideal case here. So if you are not satisfied with what I said just now, when question will tell you whether it's the other bad thing or not. I mean, that's what we learn in engineering, right? There's always an ideal versus actual case. So how do you know whether it's ideal or actual case? I will have to tell you lah. But in actual, of course, what we are dealing with mostly is actual case. Ideal case is only to estimate what is the potential of the case. So when we deal with throttling valve, ideally speaking, there shouldn't be any change in heat. Because again, it's just a flow in the pipe. But of course, we know that it will gain heat or release heat depending on what's the temperature lah. There shouldn't be any work in or work out because again, we don't supply any energy to the fluid. The fluid doesn't generate any energy. It doesn't lose any energy through, in this case, in this sense. So again, kinetic energy is insignificant, the change, and potential energy is also not significant. So you will see that when you are dealing with throttling valve, your equation is this. So when your equation is this, then what are we looking for here? If the enthalpy doesn't change. So enthalpy doesn't change, but it doesn't mean that the properties don't change, right? Because we say that we throttle the pressure, meaning if pressure change, temperature usually will change, like we mentioned just now. Usually they go together, even if they are not entirely dependent. So you can use this basically to find what are the change in other type of energy. So the overall enthalpy doesn't change, but it doesn't mean that the flow energy or the internal energy don't change. It's just that the sum of their change is the same. I mean, the sum is the same. Okay, so again, it will depend on what you are dealing with lah. So if you, let's say if you're at the table, you can actually check what is the new temperature, these kind of things. So here is just one simple example here. Of course, we are not going to ask you this kind of thing because there's nothing to see here. If you are dealing with an ideal gas, the temperature of an ideal gas does not change during a throttling because during throttling, H is a constant. For ideal gas, we know that H is Cp delta T. So if H doesn't change, Cp don't change, T don't change. Okay, so another example here. So here we are looking at what we call a mixing chambers. So in engineering application, the section where the mixing process takes place is commonly referred to as a mixing chamber. This one for mechanical engineers or mechatronic engineers, you don't use this as often. This is more used by like chemical engineers. So mixing chamber, so you mix two different things. So for us, let's say we talk about water here. So very straightforward. You know that let's say if you have hot water, cold water coming in, they will mix, properties will change in general, that's the case. So Enthalpy will also change because you have two different sources that come in here. So for this case, again, ideally speaking, if this thing is insulated or adiabatic, Q in Q out can cancel off. Again, we don't have any work out, work in. So ultimately, again, you will see that this is still a similar equation to the throttling valve. But since this is a mixing chamber, you will have two different inlet. So then you will have two different enthalpy into one enthalpy. Essentially, we are just talking about conservation of energy here, right? Energy that flows in here, energy that flows in here equals to energy that comes out. And if you incorporate a little bit more, we talk about conservation of mass, then mass in plus mass in will be equals to mass out. Yeah. So then so in this kind of situation, then you get two equations, then you can solve whatever the question asks you to solve lah. Okay, so this is the case for mixing chamber. So mixing chamber, the theory itself very easy. Just energy in equals to energy out. I mean, generally that's what we have been doing lah. Or the energy in equals to energy out. Okay, so heat exchangers. So heat exchangers are devices where two moving fluid streams exchange heat without mixing. So this is a very common thing. I think most of you would know what is a heat exchanger. So for heat exchanger, the theory itself is quite similar to mixing chamber, but not exactly the same. Okay, so mixed heat exchanger doesn't have a mixing process. So mixing doesn't take place here. So when you cancel off again, let's see what you use here first. Yeah. So for you see, if you are talking about the heat exchanger, right? So what happened here is this: you have fluid air that pass through here. So this fluid air is the cold air, cold fluid. Then fluid B is a hot fluid. So you can see here. So as it pass through here, it gets heat up by B, and then it goes out. So this heat exchange takes place here. So let's say, so this is the boundary that we set. And let's say again, once again, we assume adiabatic system lah. Meaning the heat exchange that takes place is happening inside the boundary. Meaning we don't consider any heat exchange here. So the way that we cancel everything off is the same as mixing chamber. Makes sense, right? So ultimately, what you are left with is m dot h in equals to m dot h out. The only thing that is different here is that this time the conservation of mass is slightly different. So what we have here will be this. So your mass, your energy in is actually, let's say we use this as an example since the number is 1, 2, 3, 4. So we use this as an example. So energy in is mass flow in for the 15 degrees Celsius water. Then H3 will be the energy in for the 70 degrees Celsius R1348. And then out will be 2. So 25 degrees Celsius water. M4, H4, 35 degrees Celsius R1348. So in this case, M4 is actually equals to M3, while M2 is equals to M1. So there is no mixing here. The mass flow rate depends on their own. So let's say if you are to solve this question, actually you can, because you do have water at 300 kilopascal. Pressure doesn't really change here. So here you can actually use the table for water. For 300 kilopascal, 15 degrees Celsius and 25 degrees Celsius, you can get H1 and H2. Then go to the R1348 table. You can still get the H4, H3, H4. Then you can actually solve this question. Of course, you don't have mass flow rate here lah, but yeah. So that's generally how we can look at this question. So heat exchanger, again, we just assume that the energy exchange that takes place inside is equals to each other, basically that. And we will have this kind of example in tutorial as well. You can see more. Okay, so lastly, so like I said, the last one is not exactly an example. It's just pipes and duct flow. So we are just showing you what are the possible types of things that can happen in a pipe. Okay, so there is no fixed answer to this one. So let's say in this case, transport of liquid or gases in pipes and duct is of, okay, this one is just explanation. Transport is of great importance in many engineering applications. So flow through a pipe or a duct usually satisfy the steady flow conditions. So here you can see that in this case, we are looking at this one here. So if we are talking about flow here, then let's say if you have the full equation, based on this question, if it is an adiabatic pipe, then we are cancelling off all the Q. So KE maybe not, GZ cancel, then you are left with work in. This is work in, then work shaft is work out. So it flows through, this will provide energy to the fluid and it will move this. So this is the case-by-case basis. So you need to look at what are the information given to you, then you can solve one by one. So like in this case here, you have a hot fluid flowing through, surrounding is 20, you have Q out. So in this case, you cannot cancel Q out, but you can cancel off Q in. Then there's no work based on this question. So similar thing. So what is this one? Let me see. Okay, so this is this one will be the example for this. So like in this question, again, this is we draw it like a closed system, but actually you have a flow in here, flow out here, as you can see here. So we have a flow in here and flow out. So for this question, you have energy in or work in, you have a Q out. So if you take back the whole equation, you cancel everything off, you are left with work in and enthalpy. Then Q out and enthalpy. So we assume these two negligible, there's no work out, there's no Q in. Then you are left with this equation if you are to solve this. So this equation is for if you are dealing with air. Okay, again, MC delta T, we don't use it for water. Okay, we only use it for air or ideal gas. Okay, so just one example. Yeah, so this example requires you to use this equation, which you have learned last week. Wait, so no, I was pointing at the wrong equation, sorry. This equation for CP. So okay, this CP value, it will be in terms of kilomole. You need to convert it to kg. So let's read the question first. So air enters the compressor of a gas turbine plant at 100 kilopascal and 25 degrees Celsius with a low velocity and exits at 1 megapascal and 347 degrees Celsius with a velocity of 90 meters per second. So the power input to the compressor is 250 kilowatt and it is cooled at 1500 kilojoule per minute. Determine the mass flow rates of air through the compressor. Take the molecular mass of air as 29 and allow for variation in specific heat of air as a function of temperature. So they're asking you to use this equation. This time, you don't need to go to the table because this equation is actually given to you, all the values. So all you need to do is sub in the temperature and convert kilomole to kg. So you may begin by considering the general energy equation given below. So try this out. Try to see whether you are cancelling off the proper terms for this case.
limited engineering, limited energy,人可以这么最开心，对，我才还没事情。
So again, first off, if you are easily overwhelmed because the questions has so many information, write all of them down first, like one by one, to see what you have. Group them up. Or you can do something like this. So like in this case, I'm not sure the version that I give you have this, but so you can actually write out the just it doesn't have to be proper lah, but you can actually identify like what's the inlet, what's the outlet first. Right? So here, whenever the question says something like with a low velocity, right, usually it means that it is not significant because it cannot be no velocity, right? Like velocity, we cannot just tell you it's zero because or else it's not flowing. But yeah, so usually when we say low velocity, we are asking you to assume that it is zero velocity. So in this case, these are the information that are given to you based on the question. So once you do this kind of thing, let's say, so exam, I won't give you this, but once you have drawn it out, something like this, then it becomes a bit more obvious where all the energies are going, like all the directions.
C 什么意思？Velocity。哦，velocity。没错。我看了是用 meter per second 的，不是velocity。我有很多个 V 啊，我也周末用了很多个 V。D 就要顺了。还没有去到这里，没有通顺。3点半过后回去就可以。可能需要退单。到1点了。走。哦，是啊。我忘记有开推荐册。在5点过后回来睡。中午还没有睡呢，拍照一起睡。 嗯。是。有钓鱼啊。
Okay, I think let's look at this example, then we are done with this question. This class lah. Okay, so again, we just look at this equation, all this information. So like I said, try to group all the information up first. So we have a compressor. So in this case, you are given at the inlet, the compressor has the air has 100 kilopascal and 25 degrees Celsius temperature, and low velocity. So low velocity means that velocity is 0. So in this case, this equation that they give you, they use C as velocity, so just follow. And it exceeds at 1 megapascal, 347 degrees Celsius with 90 meter per second velocity. So the power input to the compressor is 250 kilowatts. So this 250 kilowatt is input, and it is cooled at 1500 kilojoule per minute. So this is the Q out. So you have a Q out here. So determine the mass flow rate of air, and then you are given molecular mass of air as 29, and you need to use this equation. So for this question, so we'll learn this. Never mind. Alright, so in this case, the potential energy change, input heat, inlet velocity, and output mechanical work are negligible in the case of the compressor. So again, we know that for a compressor, we don't have work out. So work out definitely will get cancelled off. Potential energy, usually we just cancel off unless the question specifically requested for it. And then like I said, velocity term, most of the time we will know, but in this case, since the question gave you the velocity term, just include it, because you are given it, then just use it. Okay, so enthalpy we will never cancel off. Then we have work in here. We also have Q out. So these are the terms that we have. So after you cancel everything off, this is what you are left with. So we move H2 to the side, to this side. So m dot H1 minus H2 plus W dot 1 equals to m dot C2 square over 2 plus Q2. So this 2 is out lah. Okay, so here we have, so what information do we have here? We have Q2. We have work 1, right? C2 square also we have. What we are looking for is mass flow rate. So meaning, what we need to, so now the only information left that we need is H1 and H2. So you need H1 and H2, then you can find mass flow rate, which is what the question is asking for. Right? So how do we find H1 and H2? So again, look back at the question. What we are dealing with here is air, which is what we can assume as ideal gas. So if we are dealing with ideal gas here, so meaning you can convert H1 and H2 to CPT1 and CPT2. Okay, we can use CPT. And how do we find this CPT? So this one is the complicated side because now they ask you to use this equation. So this equation, they have integrated this for you, so you don't need to do anything to it. All you need to do is you sub in the temperature term into all the T. Okay, so once you sub in the temperature into the T, you will get a value, a new value, which is in this case 29.07, but this value will be in terms of kilomole. So you just divide the whole thing by the molar mass, you will get the value in terms of normal CP in kilogram. Okay, so this will be the CP value that you can use over here for T1. So this one, you will use this for this. Okay, so this CP value, when you use this equation, is very temperature dependent, as you can see from the equation itself. So at different temperature, the CP value will be slightly different if you use this equation. So you have to recalculate. So this one, is only specifically for T1. So meaning later you will see that for T2, then we sub in a new temperature at T2, which is this 347 plus 273. Then you will get a new CP value that you will use for this side. Alright, understood so far? So again, for this round, right, at least for this specific example, the most important part will be this part. Okay? This is just extra because you have learned that we have three methods of looking for using different CP value to find the value, to find the enthalpy and stuff. So this is just extra. So the main point will be this first part. Okay. So let's say if you are dealing with hot water, then easy. You just use the properties given, find H1 and H2 from the table. Alright. So now I move on. So second part, again, same thing. So you can see that we are using the new temperature to find a new CP value. So once you have found this, then you sub this into CP T2. So then you get two new value. So from here, you can calculate mass flow rate. So you just sub everything in, make sure the unit is the same. So this is in minutes, so you convert this to second. Then from here you can get mass flow rate. So another reminder, so you can see the velocity term also same thing. We need to divide by 1000 to convert it to the same unit. So that's why I keep stressing unit in this subject, because these things does happen a lot. But there's a lot of unit conversion that you need to do. So make sure that they are in the same unit. Okay, so after this, now that we have the mass flow rate, then what does the question ask for again? Let's go back. Okay, so once you got the mass flow rate, we are looking for nothing else. That's all we are looking for. So then that's all. We'll stop here. Thursday we'll finish this up.